All right, so let's see. So we have a training data set now, okay? We have the initial model. We know how to pass data through the model. By far the most important thing is when training a model, in this case a diffusion or a score-based generative model, is the loss function, okay? So now is finally the part where if we look at everything, if we just remind ourselves what we had here, we can finally sort of nail this block, and we're gonna have to go to the paper because I don't, writing the score-based loss, I use this, oh here it is, loss functions. So this is a good chance to talk about what do we want our loss to do. Now, if we look at the paper, it's gonna seem a bit obscure because it's, I already know it, but it's sort of, let's see, do I have a better one? Oh yeah, here it is. Equation 14 is loss train. This is pretty easy. I sample a batch of data, which we saw last time. I just take like 10 data samples, for example, a subset, right? So B is just the subset size. I add some noise to them. So Z is Gaussian noise. So my data is H, right? So I add some noise. That's easy to do. We can do that in one line. I pass it through the model. We can also do that in one line. Actually, we're gonna have to functionalize that again because we really, really want to be able to, well, no, we're gonna have to do it in real, sorry. So there's a bit of abuse in the paper here because these are complex values, but this means you pass it through the model, then you rebuild it. You take the complex data, you add complex noise, you turn it into reals, you pass it through the model, then you convert it back to complex, which is exactly why we did that whole circus earlier, right? About that whole 3-stage pipeline. Okay, then we add the noise after it's passed through the model, and we take the means, the L2 norm, which is just the sum of squared absolute values, and we multiply them with something and we average. Okay, this is easy to implement, but this is a good chance to talk about diffusion models, and I'm pretty sure they're super popular. Maybe you've seen, like, if you've even seen any of this popular AI, you know, diffusion models are super popular. They are the models that generate those images you see, like deep fakes or AI images, right? Yeah, so you may have heard of stable diffusion. And this sounds familiar. It's starting to sound familiar to the language we're using because they're just systems that create data. In my paper's case, which was many years ago, it was one of the first applications. While people were doing it on images, we decided to do it on wireless channels, but it's just another form of data. It doesn't matter. So yeah, everybody knows, well, these are pretty famous, but my paper it was so early that it's sort of a proto form of this. But okay, so what is that loss function and how does a diffusion model work? I think let's crash course it a bit, which is a nice crash course into more modern AI. So let's say I have a trained diffusion model. Okay, so there's a difference between training and using a diffusion model, right? So when we say training, this just gives us a trained diffusion model, which is just a neural network. We know what this is because we've seen it in once I'm going to split this into episodes, we've seen it in the previous episodes. It's just a neural network. Let's see, where do we have it? Oh, like here, right? That takes as input a tensor and outputs a tensor of the same shape. Now, this is a UNet, but it doesn't matter. Okay, so now you did the training, you have this. How do you use a diffusion model? That's a completely different story. Okay, so that's called, how should I do this? It's called inference or sampling. This sampling language is specific for generative models, right? So this is how you create, let's say, synthetic data, or how you use a generative model or a diffusion model or a score-based. I know my paper calls them score-based. That's sort of the older name. but it's fine. They're really the same thing, which that's a whole different discussion for another time. So the inference looks like this, roughly speaking. Let's do it this way, actually. It's a bit more complicated. And let's color this in blue, okay? And the inference involves multiple calls of the model. Okay, so the inference involves using this model, which is this blue box here, many times in sequence, okay? So it's sort of a gated process. I use the model once, then I take the output and I use it again, okay? So the processing chain will look like this. Now, we know what we want. What would you want the output to be of this? Well, obviously this has to be data, or this has to be what's called synthetic data, or realistic but artificial data, right? So these are all those images you see, like the deep fakes, or the deep fake voices, or the deep fake videos. You know, if you look at OpenAI, Sora, it's also a diffusion model. I'm not gonna get into that, but it doesn't matter. Now, the other interesting thing is that this whole process starts from noise, okay? So noise is random data, random, typically Gaussian data, okay? So for images, if we were to display this, and maybe this is a good time to also start thinking about plotting data or displaying data, it's gonna look like gibberish, right? You won't be able to tell anything. Okay, so we know what we want this to do. So what happens when you actually use a model? So what you do in diffusion is you take your initial data wherever you are in this chain, okay? So this is also called a reverse diffusion chain. That's a more technical term for it, because I want to go from noise to real data. So intuitively, the key idea is that at every step, the diffusion model is trained to remove all the noise. But what I'm gonna do is I'm gonna remove all the noise, but then I'm gonna add noise back, but less than the previous step, okay? So this kind of looks something like this. There's also an addition operation now. So I'm gonna inject my own noise back, except it's gonna be less and less noise every time, okay? And let's see if we can get a bit more room here, okay? So then we would get, after the raw model call, we would get what we would call a denoised data, or a purified data, if we want to call it that. And then we're gonna add the noise back, but not as much as it was, because here it was complete noise, right? So let's think about it this way. Let's imagine the noise is actually 1 times noise plus 0 times data, because this is what pure noise is, right? What is the other endpoint I want to get to? Obviously, this is going to be exactly the opposite. 0 times noise plus 1 times data. This is what pure data is, right? So I need to go from pure noise to pure data. Well, it's easy. I'm just going to interpolate these coefficients, okay? So next time I add noise, I'm going to add 0.97 times noise. And the idea is that magically a diffusion model should recover some data, or more and more data. So imagine this would sort of recover 003 data, okay? So now I entered the diffusion model again, but this time I enter it with noisy data. In this case, it'll be 0.97 times noise plus 003 data. And this is a sketch. The real values are not like this. It's a bit more complicated. And then this repeats. Now, next time I go through exactly this, and this is all the same model. This is very important, right? It's a single neural network that's used multiple times. So then I go in with less noise because now I've extracted more data. I go with something like 0.94 and I go ... and I end up with, let's see if we can zoom out. There we go. So then I just end up with something like 0.03. And of course, in this last step here, I'm going to have noisy data, which is going to be exactly flipped. It'll be 0.03. It's almost clean data. And that's it. I end up with pure data, right? Or pure artificial data. And it's pretty wild because, well, the whole idea is we started from nothing. Like we're not really denoising something because we start from zero data. But if you look at the image after the first step, it'll look like a very basic blobs. Like if you were to look at images after very few reverse diffusion steps, they start like blobs, right? Which is like very average looking data, and then they gain more and more structure until you actually end up with a sharp looking image. In any case, so now we know that now what we need is, in order to denoise, we need a model that predicts either the noise from data or the data from noise. Okay, so then the job of a diffusion model in training now is to take as input, what does it take? It has to take in, let's say, A times data plus B times noise, a mixture, some coefficients at all levels, right? And it can output either of them because it doesn't matter if I want to remove the noise, then an easy thing to predict is I'm just going to predict minus B times noise. And then if I add the output back, I've removed the noise. Okay? Because if I take this noisy data and now, of course, it warps the data. I mean, no, actually, this is reasonably accurate-ish. There's a few more subtleties here. I could have also predicted, so it also works the other way, I guess. So optional. We can also predict B times noise. It's basically the same thing, except I would just subtract it from the input, not add it, right? We can also predict, let's see, can we predict the data? Yes, we can also predict the data directly, in which case I don't need to do anything. But just for historical reasons, we're gonna do it the minus B times noise way. So now what is a loss function? Well, a loss function is the difference between the output and the desired output, okay? So then, finally, the loss will be model applied to noisy data, okay? So I take my noisy data, I pass it through the model, and I subtract what I want to get. But what do I want to get? The negative B times noise. So it's a double minus, okay? This is by design. Okay, which is equal to model noisy data plus B times noise. And then I just take the norm of this and I square it, and this is my loss function. So this is why in the paper the loss function is I take my data H, I add noise to it, Z, I pass it through the model, and my loss function is I take that output and I sum it with the noise times the coefficient. In this case, divided by a coefficient, but it's times 1 over that coefficient, right? That's why there's a plus here, not a minus. This may seem confusing at first, right? Because usually in loss functions, so in school, you'll learn that the loss function is output minus desired. It is like this, but except here my desired also has a minus sign. So then the shorthand way to write it is with plus, okay? And that's it. And then there's also a weighting with the noise level, which is a bit more detailed, but we have to implement this thing here. Okay, so we can finally get back to coding. Now this should be really easy now because we have everything, right? So let's write the new losses.py. Did I save? What happened here? Okay, here we go. Okay, so then what we need to do is import torch. Okay, we need to define score training loss. I'm just gonna call it like this. So what does it need to take? It has to take the model prediction, which is a tensor, and the noise, that z thing, which is also a tensor, and the coefficient, which is also a tensor. Because remember, in PyTorch, and it will return also a tensor, but it's a scalar tensor, okay? All right, so let's clean this up because it's bothering me a bit. So let's see. So if I, okay, so where am I? Oh yeah, we forgot, did we? Yeah, okay, we forgot to add this. So where are we? So we can add MIMO data and MIMO models, and we can say add Gaussian data and complex real utilities. So this is the old commit. Okay. So we can push this to simulated data. And let me check out another branch now, which is loss function from simulated data. Okay, finally, we're on a clean branch. So we want to add, I want to add it now because it's annoying me. I want to do the pre-commit thing. Okay, there we go, because it's arranging it nice for us. Okay, so now we need to implement this function. Now remember, maybe it's useful to write a documentation for this function. We gotta be careful here a bit because it's B. Because it's just one number for each data point, right? Because it's a scalar, basically. Okay. So then we can just write the loss function then, which should not be that hard. I just need to take the norm. So I have the output. Sum plus, I'm gonna assume the coefficient is squared already. So I just divide the noise and take the norm and multiply again with the coefficient. So noise divided by coefficient. Is there a way I can paste this? No, it looks horrible. Okay. So let's see. We can just return loss. I think this is pretty easy, right? So per sample loss. First I do model pred plus noise divided by coefficient. That's it. Per sample MSE. Well, actually, let's just call it loss, right? Okay. Now, the shape of this will be BH. Now, the way PyTorch works, if I remember correctly, you can divide tensors of different shapes as long as the shorter tensor matches all the dimensions. Let's check that actually. Will this work or not? So if I have import torch, so let's say I have BHW equals 10, 4, 4, okay? And I have noise torch random BHW, and I have coefficient torch random B. Can I do noise divided by coefficient? No, I can't do. Interesting, the shapes, because the shapes don't match. Well, the cheap way to do it is to add fake dimensions in the back, because coefficient dot shape is, if I do coefficient none, yeah, this adds like fake ones, and then I can divide noise with none. Kind of don't like this. Was there a better way to do this? Oh, I think there is a PyTorch functional way. Hang on, let me see what it is. So PyTorch, how to add singleton dimension. Oh, it's unsqueeze. Can I unsqueeze two dimensions at the same time? That would help me a lot. PyTorch. Unsqueeze multiple dimensions. No, I don't want to. No, we would rather do the none, right? Python's advanced sensing with none, or using torch reshape. We don't want to do, this looks really ugly. This looks uglier. Yeah, this looks cleaner. None. I guess I can reshape. No, it seems like it's still okay. Never mind. So we'll do it this way. So we have the sum then from the paper. This is still per sample. We got to take the norm. There may be some trickery here. Very careful here. Very, very careful. So if I have a complex tensor, so import torch. Let's say I have BHW equals 1044, okay? And I have data equals torch ran then BHW. Okay, so now I have data of this shape. If I do torch linalg dot norm data axis on both, this does work. So this is what I need. Is it dot square? Yes. So we need the squared norm. Does it work right for complex? Well, the easy way... Oh no, sorry, I forgot to do complex. Damn it. Okay, here's the trickery. So if I do d-type torch complex 64. Okay, now will the norm work? I don't think so. It still works. And does it look right? Well, there's a manual way. So manual norm is, we just do it the crude way, because we do torch sum of squares of absolute values of the data squared. So summing squared absolute values on dimensions -1 and -2 on the last two axes. Manual norm versus, yes, okay, it's the same. Okay, so then we can just do torch linalg norm from the loss on axis -1. It looks cleaner this way than to, and dot square. Okay, we're almost there. And then we do weighted loss. Now, what does the paper say? We have each norms, but we have to re-multiply with the coefficient. Remember, we're assuming this is the coefficient. It's already squared, right? Well, that's really easy. So we just do coefficient times loss. Okay, then what? We just take the average, sum and divide by number of elements, okay? So that's it. So average loss is torch.mean weighted loss, because now it's a scalar, return average loss. Okay, so we're done with the, it took us more time to write the, but this is fine, all right? So now we implemented equation, whatever it is from the paper. Okay, so we implemented the loss function. Let's test it. Let's go back to our model now. So let's grow this thing here. Well, actually, no, let's not go back to our model. Now we can go back to our main. Actually, we should move this stuff. We played a bit with the model. Let's not play a bit with the model here. Okay, we can finally start writing main code here. We're not gonna need this matrix multiply. It's too basic. Okay. We can also move the imports. Torch. Oh, we have torch. That's good. Yes, I need these. And I think that's all I need. Oh no, sorry. I need from MIMO models import get unit config because I'm not here anymore and get model. Okay. And that's it. Yeah, that's it for good. Now, if I run the pre-commit, it should clean all the unused imports for me. Yes, it does. Okay, good. Nice. Everything is clean. No more errors. Good. So now we just moved everything to mains because I can just run MIMO main now. And actually, let's do a trickery here. Well, let's commit this. Start see MIMO losses. Because we don't really need a main. Okay. Well, actually, what we should do is just rename this file train. Because this is what the main is, at least so far. And then we can just do git commit add loss function. Okay, then where are we here? Git rm source MIMO main. This should just be a clean replace in GitHub. And git add MIMO train. Okay, so it's just a rename main to train. Nice. Okay, and let's see. Okay, so now what does our train do? Well, we need to bring the loss function in here, obviously. So we're gonna do from MIMO.losses import. Well, what do we call it? Score training loss? Okay. And let's also prepare the coefficients. So what else do we need here? We're gonna write a tiny function will be add noise to data. I don't even think it's worth it, but let's just add it, right? So coefficient torch tensor. We have to be a bit careful here because now when we say we add noise to data, we want to say power. Noise has power and it returns a torch tensor. There's a tiny trickery here. Noisy data, okay? So then we'll this is a 2-line function, but I like to keep it modular. So first we're gonna sample noise. So we can say noise equals torch random like data. This is a neat PyTorch trick. This automatically gives you data, random data of exactly the same shape and type like your data, okay? And then we'll just do let's do standard deviation. Okay, so it's standard deviation. Now the only annoying thing is, again, we need to do this. And then we can just, we don't even need to type this. We can just return data plus noise directly. Okay. Well, actually, I don't like this. Let's do it this way. So noisy data is data plus noise. Return noisy data. Okay. This is easy. There is, again, yeah, let's do it this way. It's fine. Okay, so then we do score training loss, and we also need from MIMO.losses import add noise to data. So we get the model, display is fine. We get the data, so this is clean data, okay? Let's run some noisy data through the model and get the loss function without inference mode, because we want to actually head towards training. So we get the subset of data Here it is. So data subset, we just have to interject ourselves with noise here. Aha, I know a trick here. And we're gonna want this function to also output the noise, okay? Because we're gonna need the noise in the loss function. Oh, this is why, okay, this is good. It's a good thing we did this function. So we're gonna simultaneously add noise to data, to this data subset. Now, what coefficient do we need? Well, let's sample some random noise powers too. Now, these are torch rand. I can't use random. Noise power can only be positive, not negative, or no, the noise standard deviation, which is the square root of power. So gotta be careful here. So we can just sample from 0 to 1, right? And we'll just sample how many? The shape of the data, right? The first shape of the data, because that's the batch size. Okay, so we add it with this standard deviation. It gives us the noisy. Now the real comes from the noisy, okay? It goes through the model. It gives us the output. Then we need to compute the loss function. Okay, so then we have loss equals, what do we call it? Score training loss, okay? So model prediction, output, the noise we originally added, which is finally why we had to return it, and the coefficient, which is the squared standard deviation, dot square, right? Because that's what the paper says. Sigma is the standard deviation. The power is the square of sigma. So this is the only trickery here. When we add the noise to data, we multiply it unsquared on the outside. But then in the loss, it becomes squared. And that's it, we can print. Loss function on this, on batch, is loss dot item. Okay, let's see. UV run pre-commit, run all. UV run -m, MIMO dot train. Now this doesn't actually train because we didn't do the optimizer. Training is a bit more complicated, but okay, I forgot. Why? Where? Oh, my coefficient. Damn it. So device equals data subset dot device, obviously. Everything has to live on the GPU, all right? Okay, again. Every time an operation happens in PyTorch, it goes through. There we go. So input shape is 10, 16, 64, complex 64. We add noise. Doesn't change the shape. We pass through the model. We get the loss, which is finally just a number. So the goal of training is to minimize this loss, which we just got. And we're done. Now we have a full loss function. That's it. That's for losses. Then, so next episode we'll do an optimizer, and we can actually train a model. We're getting way closer.